Hello folks, in this video we will be talking about properties of waves. Light is a wave of perpendicular oscillating electric and magnetic fields. That's a mouthful there, right? So we've got the blue sine wave that's in the XY plane representing an electric field. And we can see the blue electric field vector oscillating up and down. And then perpendicular to that in the XZ plane, we have the oscillating magnetic field. And these two are all propagating forward in the X direction. So that's our direction of propagation there. So the electric field and magnetic field vectors are perpendicular to each other, and they are perpendicular to the direction of propagation. And then we can write that more succinctly, saying that our E field is perpendicular to our B field, which is perpendicular to our velocity arrow, the velocity of the wave. Let's talk wave vocabulary. We've got a picture of a wave up there, which has its crest and trough labeled, the crest at the top, the trough at the bottom. A full cycle is where we go through a whole repeat. So this is just half a cycle going from this point over, and we need the rest of it to be a complete cycle. We need a wavelength is crest to crest distance or trough to trough distance. The amplitude is from center up, and we're showing the direction of travel to the right. I have a table where we're going to define all of these physical quantities and a few more. We'll write the symbol for them, and we'll mention what their units are. Let's go ahead and get started with that. Our first physical quantity is amplitude. Amplitude is used, the capital A is our symbol for amplitude. Its definition is the height of wave from the center up to the crest. So it's not the trough to crest distance, it's the center to crest distance. And its units are in meters, and the symbol for meters is M. Our next quantity is wavelength. We use the Greek letter lambda to represent the wavelength, and it is the distance or the length from crest to crest, from trough to trough, or any two similarly corresponding points. The distance for wavelength is in meters per wave, which we often just call meters because wave isn't a unit of measure. We have frequency, F. Frequency is the number of complete oscillations at a point that go through in 1 second. So it has units of waves or cycles per second, which is also just 1 over seconds, which has the name hertz or capital HZ. We also have the quantity period, which its symbol is capital T. This is the time for one full wave pulse to pass by. And because it's an amount of time, its units are seconds, or in particular, seconds per wave. There we go. And then the last quantity in this table is the speed. This is also sometimes called the wave speed. I've seen that both as two words, wave space speed, and wave speed all as one word. Symbol V is like always for all of our speeds. And it's the distance that a wave covers in a given amount of time, as any good speed definition ought to be. And so it has units of meters per second. It's distance per time. Those are our vocabulary terms for waves, for describing the properties of waves. We have two equations that are useful. The first one here is that the period and frequency are inverses of each other, right? Period is the amount of time for one wave, and the frequency is the number of waves that pass by per time. So time per wave, waves per time, they are inverses. Let's consider just one cross section of the overall wave. We have these oscillating electric and magnetic fields as shown. In this example, let's assume that it takes an oscillation a half of a second to go down and back up for the electric field, or all the way to the left and then back to the right for the magnetic field. In other words, if it takes half a second to complete one cycle, we're going to complete a whole 2 cycles in a full second. So our time period is half a second. The frequency is 2 cycles per second, aka 2 hertz. And so that shows the inverse relationship between period and frequency. The other equation here that's relevant for waves is speed is equal to wavelength times frequency. And to justify this, we're going to look at the units. On the left, we have how fast in meters per second. And then wavelength is meters or distance per wave. And frequency is number of waves per second. We see that the waves cancel out, and so our units match up to give some justification for this relationship. But also, we think about the meters of distance that one wave covers multiplied by the number of waves that pass by each second. That's going to tell you how fast your wave is going. And for electromagnetic waves, which are the waves that we will be studying for optics, that speed in a vacuum is, we use the letter C for that speed, and it's 300 million meters per second, or 3.00 times 10 to the 8 meters per second. So in this example, we can see down here, it says, speed is constant. The speed of light in a vacuum does not change. So there's an inverse relationship between the wavelength and the frequency. Bigger wavelength means shorter frequency, and faster frequency or higher frequency means smaller wavelength. Modeling waves with equations. So this is going to be our sines and cosines that will plot out the sine and cosine graph we saw on our first slide. So we can plot and write equations for the electric field as a function of position, so a single snapshot in time, or we can plot a single electric field vector, so not the whole wave, just one vector in that wave, and we can see how it changes over time. So this is a fixed position over time. That's our second one here. The first one is a fixed snapshot in time for all of the positions. We can do one or the other. And so number one here in orange, this is what your electric and magnetic fields as a function of position might look like. We can see the crest-to-crest distance represents the wavelength. This is opposed to number two, is showing what happens if two individual vectors, we want to watch them evolve over time. So we can either watch one vector as time moves on, or we can look at all of them at one fixed point in time. Here we have the two graphs showing what I mean. So the top graph, try to ignore the animation at the bottom graph right now. The top graph, these are both slinky waves, by the way. And the top graph shows the slinky wave as a function of x position. And so we can see the yellow there maps out the function, or maps out the wave as a function of position. That's what the yellow curve here does. And we see it's not oscillating because this is just one snapshot. We look at the whole wave over one snapshot. All right, we can look at the more eye-catching bottom one now, where we have not one, we're only looking at the yellow dot now. We're not looking at every single point on the wave. We're only looking at the yellow dot, and we're plotting how it evolves over time. And you can see the yellow trace on the sine curve match out that oscillation with the yellow point on the vertical axis. So we can look at the whole wave at one picture on top, or we can look at a single point on the wave as it goes back and forth over time. When we're plotting against position, which is what we're seeing here, then the crest-to-crest distance on that graph represents wavelength, or the trough-to-trough distance represents wavelength. So when we're plotting wave versus position, the crest-to-crest distance is wavelength. That's opposed to if we're plotting wave as a function of time, the crest-to-crest distance on that graph isn't the wavelength because we're not looking at the whole wave. Instead, we're looking at just the snapshot of how that yellow dot on the left goes up and down over time. And so the crest-to-crest distance on a wave time graph is going to be the time period, not the wavelength. So look at what's on your x-axis before you say that the crest-to-crest distance is wavelength or time period. It depends on if you're graphing the whole thing over time or over position. So let's do an example for what this looks like for electric fields as a function of position first, and then we'll look at an example for an electric field as a function of time. So here is the wave that we are going to plot, and in particular, I sketched it here on the right. We can see that we go up to the peak electric field here. The amplitude we'll name capital E subscript 0. The units for electric field are either newtons per coulomb or volts per meter. Those are equivalent units. And this is our wavelength lambda, and we know it's a wavelength, not a time period, because we're plotting against position. The graph, or the equation for this type of a graph, might look like this. Your electric field as a function of position x is your amplitude, E subscript 0, times the sine of 2 pi over the wavelength multiplied by position. So this is what your field as a function of position graph looks like. I want to point out that I chose the sine function because it started at the origin, so that's going to be sine, and it's a positive sign because it went up from there rather than down. Now let's do another example, this time for electric field as a function of time. In this example, we're not looking at the whole thing, we're looking at just one individual vector, one slice of the wave, and we're watching it as time goes on. And if we do that, starting maybe when the E field's at the top, the graph would look like this. We started when the E vector is all the way up here, it goes down, it comes back up. And the crest-to-crest distance here is not wavelength, it's now time period, because we're not looking at actual physical distances, we're looking at for how much time passes between oscillations. And the equation that describes this graph might look like this. We've got our electric field as a function of time now, not as a function of position, is equal to your electric field amplitude, E subscript 0, times the cosine of 2 pi over t, capital T that is, for the time period, multiplied by an arbitrary time, lowercase t. And since frequency and periods are inverses of each other, you can also write this as your amplitude times the cosine of 2 pi frequency times an arbitrary time, lowercase t. I used cosine for this graph because it started at the amplitude. It didn't start at the origin, and it started at the positive amplitude, so it's a positive cosine, not a negative cosine. I do want to point out that, like all waves, electromagnetic waves can be modeled with either sine or cosine graphs and with either positive or negative amplitudes. So here we see the parent functions for y of t equals sine and negative sine of t on the top. On the bottom, we've got the parent functions for y equals cosine t and negative cosine of t. Your electric field versus time or electric field versus position graphs may take on the form of any one of these four. So it's always sine, it's always cosine. It just depends on when you started collecting data. And in fact, they could be shifted anywhere between these two, but for our class, we'll pretty much stick with these four. So you will be the one who chooses, is it a sine or cosine graph, and is it a positive or negative amplitude? All right, here's the practice. We'll talk about the answers in class together, but I want you to fill in the table for the two electromagnetic waves that are given. I want you to write units next to every number value when you do that. So we've got an electric field versus position for A, and we've got an electric field versus time for wave B. But I want you to tell me for each of those two waves what their amplitude, period, frequency, wavelength are, and then I want you to write equations versus both position and time for each. Keep in mind that the speed of the wave is c, the speed of light. And then we've got the speed equals wavelength times frequency equation. That's how we're going to translate between field versus position and field versus time graphs. All right, that concludes this video. That's our quick recap of all things waves. Looking forward to the next video.